Alright, our objective here for the speed of electrons in a circuit. How fast do the electrons actually move through the circuit? In a current-carrying wire, collisions interrupt the motion of the electrons, so their actual drift speed, or net speed through a wire due to the field is extremely low. When you flip on the light switch on your wall and the circuit is completed, the light bulb appears to glow immediately. Energy is transported through the connecting wires at nearly the speed of light. The electrons that make up the current, however, do not move at this high speed. The electrons inside a metal wire have an average speed of a few million kilometers per hour due to their thermal motion. So this does not produce a current because the motion is random. There is no net flow in any one direction. So the currents are just moving all around between those valence electrons. When a battery or generator is connected, an electric field is established inside the wire. A pulsating electric field can travel through a circuit at nearly the speed of light. The electrons continue their random motions in all directions while simultaneously being nudged along the wire by the electric field. The conducting wire acts as a pipe for electric field lines inside the wire. The electric field is directed along the wire. The electric field lines between the terminals of a battery are directed through the conductor, which joins the terminals. Conduction electrons are accelerated by the field. Before the electrons gain appreciable speed, they bump into metallic ions and transfer some of their kinetic energy. So before they get up to speed, there's a collision. And whenever there's a collision, you're going to lose some energy. Unless it were perfectly elastic, but that doesn't actually happen in the real world. Collisions interrupt the motion of the electrons. Their actual drift speed, or net speed through the wire, is extremely low. So they're moving along really fast, and then they collide, and then they go backwards, and then they collide, and then they go forwards, and then they collide and go backwards and forwards. And this kind of motion keeps happening. But if you minimize all of those back and forths and all the collisions, it appears like they are just moving along like this, pretty slowly. In the electric system of a car, electrons have a net average drift speed of about 0.01 centimeters per second. The solid lines depict a random path of the electron bouncing off of atoms in a conductor. The dashed lines show the exaggerated view of how this path changes when an electric field is applied. The electron drifts toward the right with an average speed of less than a snail's pace. So the electron's going really fast forward, here, 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 here. But basically, the drift speed, the net speed, when you add and subtract all of the forward progress, it is going to go to the right from the starting position to the ending position really slowly. Or the dashed lines, the exaggerated view, from the starting position to the ending position really slowly. In any AC circuit, the conduction electrons don't make any progress in any direction. In a single cycle, they drift a tiny fraction of a centimeter in one direction, then the same distance in the opposite direction. This back and forth motion, this is called oscillation. So they oscillate rhythmically about relatively fixed positions. They're not moving a whole bunch. On a conventional telephone, it is the pattern of oscillating motion that is carried at the speed of light. Conventional telephone, those are the old telephones that plug into the wall. There's actually a small electric current that is used for those telephones, and that's what we're talking about here. The electrons in the wires vibrate to the rhythm of the traveling pattern. So, why is the drift speed of electrons in a current-carrying wire extremely low? Should be able to answer that now.